Hello, hello, hello. Today I just wanted to talk about the cross product because in the last video I talked about the dot product. And I wanted to, again, give some motivation, at least for the definition of the cross product and show that the geometric definition and the matrix definition are actually saying the same thing. So the cross product is different from the dot product in that the cross product is a vector and the dot product is a scalar. Remember, the dot product tells us how much of one vector lies in the direction of the other. The cross product here is going to be concerned with something different fundamentally. So let's say we have a vector A and a vector B. And now let's consider the parallelogram spanned out by vectors A and B. So what do I mean by that? I mean that if I were to take this vector here and I were to replicate it so that I get this. Oh, no, that's a little bent. You know, the shapes tool should be a little better. And then I were to take this vector and then replicate it, then I would get this here. And so I would get this parallelogram here, and let's call the angle between these two vectors, let's call it phi. And so the cross product is fundamentally concerned with, well, what's the area of this parallelogram? So the definition geometrically of the cross product, it's defined like this. The magnitude of vector A cross vector B is the magnitude of vector A times the magnitude of vector B times the sine of theta. And so it's very similar to the dot product, except it's got a sine instead of a cosine. And so if we instead, same thing, we imagine this to be vector A, and we imagine this to be vector B, and we could draw a line down here. And so this, this line here, and I should have wrote sine phi instead of theta. Normally you use theta, but I'm using phi. The blue vector that I have drawn is the b sine phi. That is the length of that blue vector. So if I were to take this number here, it's a scalar, b sine phi, and I were to multiply it by the magnitude of vector A, well, look at it. I mean, vector A is literally just the base of this parallelogram, and vector B sine phi is just the height of this parallelogram. So the cross product is literally just base times height. That's all it is. And so it gives us the area of this parallelogram. Now notice I said that the magnitude of vector A cross vector B equals this schmozkin here. So that implies then that the actual vector A cross vector B is a vector, not a scalar, because the magnitude of it is a scalar. So the thing itself would not be a scalar. And so another thing that comes up sometimes is, let's say, oh gosh, this will be interesting for me to draw, but let's say we have, all right, the tools, it's not going to help me. So we have a parallel pipe head. A parallel pipe head is just it's a three-dimensional parallelogram. Basically, each side is a parallel. Each face is a parallelogram. And let's call. So we have three vectors. We have one going here, and let's call this the x-axis, the y-axis, and then this is going up in the z-axis. And so, I don't know, let's take this to be vector A, vector B, and vector C. So the angle between vector A and vector B, call it theta, I guess. And then the angle between vector C and vector B, in other words, the reference angle, how is it to the z-axis? How is vector C to the z-axis? We'll call that angle phi. And so what I'm going to claim is that the volume of the parallel pipe head spanned out by these vectors. In other words, I'll try to draw it, but so we have this parallelogram face out front, and then we have that parallelogram, and then that, and then that. Hopefully you can see that that's a parallelogram. It's poorly drawn, but hopefully you can tell that that's what it actually is. So what I'm going to claim is that that is the volume is, it's vector A cross vector B I think dot vector C. So the area of the parallelogram of the base is, of course, I think that's it. Is this base right here is as I showed before, is just the magnitude of vector A cross vector B, this base of this parallelogram on the bottom here. And if I dot that with vector C, then that is, let's see, that is the magnitude of the base, or just the base, because that is vector A cross vector B, times the magnitude of vector C cosine theta, or C cosine phi, C cosine phi. So C cosine phi, what is that vector? C cosine phi if I took phi to be, oh gosh, I just wanted that one little bit erased. If I took phi to be, instead of the original angle between C and B, if I took it C to be, or if I took if I took phi to be the angle between C and the z-axis, so this is the x-axis, the y-axis, and then the z-axis up here. If I took phi to be the angle between C and the z-axis, then C cosine phi would be this blue vector right here. So what that tells me is that C cosine phi is just the height of the parallel pipe head. And so we just have the base, the area of the base, times the height, and that gives us the volume. So if we think of the sides of a parallel pipe head as vectors, we can take the cross product of the sides that make the base and dot that with the height vector, and we will get the volume of the parallel pipe head. So one other thing that I would like to mention is that a lot of times you'll see the determinant, or see, I'm giving it away. You'll see the cross product defined through a determinant, and I want to show that this geometric way of thinking and the algebraic way of thinking are the exact same definitions. So if I go again and consider back to this parallelogram here, the area of that parallelogram, call it P, and I square that. If I take the area and I square it, then that is the magnitude of vector A times magnitude of vector B times the sine of phi, and then I would square each one of those. And so that is equal to the magnitude of vector A squared times the magnitude of vector B squared minus the magnitude of vector A squared times the magnitude of vector B squared times the cosine cosine squared of phi. In other words, I just turn this sine squared phi into a 1 minus cosine squared phi. And now notice that right there is the magnitude of vector A squared, the magnitude of vector B squared, minus, and then this is just vector A dot vector B squared. Okay, and now this becomes, if I take the square of the magnitude, that's just the same thing as adding up the components of this vector in the x, y, and z direction, since the cross product is only defined, well, at least in 3 dimensions. There's actually a 7-dimensional cross product, but that's not what this video is for. So since the magnitude of vector A is the square root of a sub x squared plus a sub y squared plus a sub z squared, where a sub x, a sub y, and a sub z are the components of vector A lying in the x, y, and z direction. If I were to just take the square of that, then I would just have what's inside of the square root. So in other words, I would have a sub x squared plus a sub y squared plus a sub z squared times b sub x squared plus b sub y squared plus b sub z squared. And now if this vector A dot vector B, when I square that, in other words, I'm taking vector A dot vector B with itself. And so what I can then do is say, well, that's just the same as if I were to do the piecewise definition of the dot product. I could make it a sub 1 b sub 1 plus a sub 2 b sub 2 plus a sub 3 b sub 3, and then square all that. And now through a bunch of algebra, because now we've turned it, sorry, I went to ones. A sub x, b sub x, a sub y, b sub y, a sub z, b sub z. Okay, so all I've done there is the piecewise product definition of the dot product. So now, if I expand this out, okay. Oh gosh, where do I want to start? Okay, well, let's just go to town, I guess. So a sub x squared, b sub x squared, plus a sub x squared, b sub y squared, plus a sub x squared, b sub z squared, plus a sub y squared, b sub x squared, plus a sub y squared, b sub y squared, plus a sub y squared, b sub z squared, plus a sub z squared, b sub x squared, plus a sub z squared, b sub y squared, plus a sub z squared, b sub z squared, minus, now I gotta square all that. Okay, I'm gonna do it though. I'm gonna square it all. Okay, first I probably am going to do the foiling on this page here. So a sub x, b sub x, plus a sub y, b sub y, plus a sub z, b sub z, times itself, a sub x, b sub x, plus a sub y, b sub y, plus a sub z, b sub z, which is a sub x squared, b sub x squared, plus a sub x, b sub x, a sub y, b sub y, plus a sub x, b sub x, a sub z, b sub z, plus a sub y b sub y a sub x b sub x plus a sub y squared b sub y squared plus a sub y b sub y times a sub z b sub z plus a sub z b sub z a sub x b sub x plus a sub z b sub z times a sub y b sub y plus a sub z squared b sub z squared. And that's all being subtracted from this schmozgen. Wow, okay, all right, well, okay, so I notice at least that since all of this stuff is being subtracted, then this and that cancel. I think all the squared terms are going to cancel, I hope. This and that cancel, and a sub z, that cancel. So those three cancel at least, that's nice. Now, okay. So I have this, and this. Yuck. Yuck, yuck, yuck. Okay, well, I want this to become, what I want is a sub y b sub x minus what I want is a sub y b sub z minus a sub z b sub y squared plus a sub z b sub x minus a sub x b sub z squared plus a sub x b sub y plus a sub y b sub x squared. That's what I want. Now, how can I get that? Okay. Well, let's just see what I can do here. I have a sub y b sub z. I need a sub y squared b sub z squared. Where is that? A sub y squared b sub z squared. That's right there. Now, I need a minus. Well, I also need a sub z squared b sub y squared. That's right here. I need a sub z b sub x squared. That's right here. And I need a sub x squared b sub z squared. That's right here. I need a sub x b sub y squared. Or a sub x squared b sub y squared. That's right there. And a sub y squared b sub x squared. That's right there. Okay. So I have the squared pieces at the end of this. Now I need the middle terms, which are all going to be minus signs, which is good because all of that is really a minus sign because of this right here. So now what I need to do is I need to get these terms here. I need a from this first bracket, I need a minus 2 a sub y, a sub z, b sub y, b sub z. So I'm looking for an a sub y, okay. So I'm looking for a sub y, a sub z, b sub y, b sub z. That would be this a sub y, b sub y, a sub z, b sub z. And okay. Where else? It's also right here. I have two of them. Okay, awesome. Now I'm looking here for a minus 2 a sub x, a sub z, b sub x, b sub z. And so that is here and here. Awesome. That worked out. And then my last two, I really didn't think that. I thought for sure I'd mess up on the algebra somewhere. So that's now we're looking for minus 2 a sub x, b sub x, a sub y, b sub y. And those are here and here. So it is actually true that all of this schmozkin simplifies to this schmozkin, which is actually written very nicely, because now all of these are going to tell me that the area of the parallelogram, remember this whole thing is the area of the parallelogram squared, is equal to that big circle that I just squared. And so that would imply that the area of the parallelogram itself, which is the magnitude of vector A cross vector B, would be this. It would be a sub y, b sub z minus a sub z, b sub y, comma, a sub z, b sub x minus a sub x, b sub z, comma, a sub x, b sub y, minus a sub y, b sub x. Sorry, this should have been a minus. And so if we write that as a determinant, that is if I had the vectors I, j, k, and a sub 1, a sub 2, a sub 3, b sub 1, b sub 2, b sub 3. Because if I, for the first right here, if I expand by minors along here, then I switch to 2's again. My bad. This should be, let me just write it again. I don't know why I keep doing that. A sub x, a sub y, a sub z, b sub x, b sub y, b sub z. So if I were to expand by minors along here, I would get my a sub y, b sub z minus a sub z, b sub y. And if I were to expand along minors here, I would get my a sub x, b sub z, minus a sub z, b sub x. Okay? And likewise, along here, I would get my a sub x, b sub y minus a sub y, b sub x. And so the determinant is a compact way of writing all of this schmozkin out. instead will make it much more nice to write and deal with. So since the area of the parallelogram squared was all of this stuff, then the area of the parallelogram itself would just be taking the square root of each one of those. So this is how you'll